Good afternoon, everyone. In the next hour and a half, we're going to explore an area of, which I've been looking at for a while now, for a few years, to do with semantic text similarity. What I'm going to do is the format of the presentation will be kind of semi-formal in a way, so I'll kind of walk you through my exploration of this space. There is some code. However, I've just noticed that it's going to be difficult for you guys to probably, run the code interactively as I kind of embark on the tutorial. So I think I've sent all the information on the repo, where the code is located. I think that's on Stark. So you guys can have a look at that code then. But what I'll do is I will be running the code during the tutorial. I'm going to spend the first probably half of the tutorial just kind of walking you through, the things I've found in this space, my own sort of research, semi-research in the area, and my findings. And then towards the end, we'll I'll kind of run through a bunch of demos, about 3 demos, where I will try to illustrate, my findings essentially in this area. So I guess without any further ado, the agenda will be as follows. So as I indicated, we'll start off with a very quick intro to the space, and then I will sort of explore what is semantic text similarity, and what does it really mean. And then we'll sort of kind of spend some time looking at how to compare documents, actually precisely sentences in this case, so anything that's essentially nothing more than a maximum of 50 tokens. And then we'll spend some time then looking at some basic NLP pre-processing steps required. And then we'll then kind of dive into some sort of feature engineering steps that are required in order to convert text into a form that allows it to be processed by a machine, essentially embedding. And then we'll then kind of delve into how you can visualize embeddings. These vectors, how do you actually, how can you visualize what is essentially a high-dimensional vector and then sort of kind of reduce it to 2D so you can visualize it. And then we'll kind of have a look at some of my demos, and then, we'll have a Q&A. So that's the plan. So, introduction. I got involved in this space because I was working on a problem which required a solution for one to be able to compare CVs against job specs. And typically CVs are these huge documents, and job specs as well are kind of huge documents, but they all kind of both are composed of sentences. So I was trying to find a way that can allow me to match jobs to CVs, and that's kind of how I got involved in this. As we all know, being able to compare text is critical and is actually growing. As we all know, NLP, that space is just kind of growing exponentially because a lot of our data actually is in textual form. So typical areas where this is kind of use will be recommendation systems. Search engines use a lot of sentence, actually involves a lot of semantic text similarity, for building a search engine. News aggregators as well kind of use this technology. And then, as I said earlier, automated recruitment systems, again, this is being able to compare text, is a precursor to being able to actually build a recruitment system. And of course, the folks who do a lot of work in the biotechnology space, folks who build solutions around drug discovery, and folks who are looking at DNA structures, etc. Again, they do actually utilize a lot of text similarity computations. And there's a whole bunch of areas that require this sort of work. So it is quite an interesting space, at least I think so. So, what is semantics? What do we really mean by semantics? So, this slide is just kind of giving you an insight into 3 sentences Two of them are kind of similar, one is not. So so first one is saying, how are you? And the guy on the other end is saying, great. And then you've got another sentence which says, how old are you? And of course, the answer is, I am 20 years old. And then you've got the third sentence, which indicates, what is your age? So out of those three sentences, which are questions, if you were to compare the first one, say if you were to compare how are you with how old are you, clearly, when we speak, we know that those are two distinct sentences. They both have two distinct, different semantic meaning. And how do you train a machine, to be able to do this? So that's really the whole essence of what this work is all about, is being able to give a machine enough intelligence so that it can look at text and begin to start to infer semantics out of text and thus provide meaning in text. So again, these are just some definitions I kind of scraped from Wikipedia. So, STS is a solution that obviously deals with determining similarity between text, as I indicated earlier. Generally, I've kind of narrowed this down just to sentences, phrases, and maybe paragraphs, but not huge documents. Yeah, those will require different kinds of solutions, maybe text summarization, etc. But so this is all about just kind of, as I said earlier, sentences which typically have a maximum of maybe 50 tokens. Yeah, this is where you typically want to use this kind of technology. And then there I've got a Wikipedia definition just indicating that STS is based on the likeliness of their meaning or semantic content, as opposed to lexicographical apologies for my pronunciation there. So essentially, it's not just about the text or the structure of the text, it's really about meaning. So in fact, you can have two sentences that completely have different tokens, but they actually mean the same thing. So it's all about being able to find semantic meaning in text, which actually is not as easy as one might think. As I indicated earlier, this area is a growing space. Some of the key players in this space, the usual suspects, Google, Microsoft. My sort of involvement in this, I realized that some of the latest technologies that have come to light have really come from some of the things that Hugging Face have been doing. And in fact, a lot of the recent language models are out there now. Most of the most powerful ones are coming from Hugging Face. And I've had a chance to play with some of these and compare one against the other. Another thing that has been going on for a number of years in the sort of research domain has been this whole area called, it's called SemEval, where they look at a bunch of what they call STS benchmark problems. So these are problems which involve things like, a question and answer type questions, where you have a question and answer. Are the questions duplicates or not? Again, that requires being able to measure similarity. Another one is where they have sentences or sentence pairs, where you're trying to kind of compare one sentence against the other. Are they the same? And then the good thing with that is they also provide a label, so they tell you what the correct answer really is. And then, so then you can build a model and then compare that model, your model, against their findings, and then you can then use that to kind of validate, if your model is actually performing accurately. So, as I indicated earlier, I've got 3 demos that I'm going to present. The first one would just kind of give you a very brief look at what are the metrics one would use to compare sentences. So things like cosine similarity, Euclidean, distance measure, and Jacquard, similarity. Then the second demo is where I've built a very, very kind of toy sort of search engine, again, based on here's a corpus of sentences, and then here's a query. How close is that query to all the sentences in the corpus? So, that's... And then the third one is kind of where I've basically done a comparative analysis of looking at a bunch of embedding techniques. So from the very basic TF-IDF to the more kind of contemporary transformer-based models. And I've kind of given some numbers on which ones perform better. So we'll kind of get back to this later on towards the end. So I'm going to start off by just kind of walking you through some of the ways to measure sentence similarity. So as I indicated prior, there are a whole bunch of metrics one could use for measuring sentence similarity. In my work, I've just looked at 3. So I've looked at Jacquard, I've looked at cosine, which is quite popular, and I've also looked at Euclidean. And then out of the 3, I've kind of selected the one which I think kind of performs the best. So if we start off with Jacquard, what is Jacquard similarity? Jacquard, actually, when I first encountered Jacquard, I was trying to solve that same problem. Yeah, so I'm trying to compare CVs, one CV against a job spec. And I tried out a whole bunch of other models, and I actually then realized Jacquard. And I realized that Jacquard, you don't need to encode it per se. You can just take the sentence in its natural form, tokenize it, and then basically just do just compute, the intersection of all the, the sentence A against sentence B divided by the union of both sentences, and that kind of gives you a score. And that's precisely what Jacquard similarity is. It's a very cheap way to, to kind of measure similarity between tokens, but it doesn't codify semantics in any way. It's a completely mechanical thing. So that's the problem with Jacquard, but it's a good start. And again, here you can see it's pictorially what's going on. So basically what we're saying here is that we're looking at the intersection of 2 sets, and then we're counting how many items are intersected, divided by the total number of all the items that are unioned. And that gives you a score. The next one is Euclidean, which is very popular in machine learning. So we use this a lot to measure all kinds of use cases where there's distance. Again, one could use this metric. Again, in this case, you would have the two metrics. The two sentences, and you basically will do a norm of the two, and that will give you a number. It usually is very sensitive to scale, so it's something to bear in mind that it's very sensitive to scale, which is probably why it's not very popular in the NLP space. But it has been used and can be used for measuring similarity. And then, of course, the one that's the most popular way of measuring similarity is the cosine similarity metric, which, again, you can see that mathematically what's going on is you've got A and B. You do the dot function of A and B divided by the norm of A and B, and then basically that gives you a number, but that's between -1 and 1. And then you can use that as a metric for measuring similarity. Let me just pause for a minute on that. Any questions? Okay, cool. So now, as I said, I've got 3 demos. So here's the first one I did, which is, and I'm just going to present the findings, but later on I'll actually run you through my code. So here's the first one. So here you can see that we've got a query. Yeah, it's a simple query. It's just, actually, this is one of the demos called the book title demo. So all it is just a list of books that I got from some source online. And they just, the data set actually, it's got a lot of other columns, but I've just pulled out the title column. And in there, what I'm doing is I'm basically saying that if I take one title, I want to compare that one title to the rest of all the titles in the corpus, and then to see how close is that one title to the rest. So in this case, the query is what you see there, Hitchhiker's Guide to the Galaxy, blah, blah, blah. And then I'm basically comparing it against the rest of all the titles in the corpus. And then, obviously, in the interest of time, I'm not displaying everything, so I'm only just displaying the top 10, I think, or top 10 in this case. And there you can see, so the first two are very close because they're basically the same thing. And then you can see how all the three different metrics, how they've, what the outcome is for each three of the. So for the first two, they all match exactly, which is great. And then as you can see there, as you look at the third and the fourth and so on, you can see that there are variations in how one will, in the outcome of Jacquard versus Euclidean versus cosine. Yeah? So again, this is just one way one could, measure similarity. Any questions on this one? Because I know I've kind of rushed through that a little bit. Yes, thank you.
So what we're reading, Bill Bryson's African Diaries, what we're reading is Jacquard is because that's only lexicographical, and Euclidean and cosine, that's because it's
Correct,
semantic.
correct. Precisely that, exactly. Okay, any other questions? Yes.
Yeah, so in other areas of kind of signal processing and so on, you go from Euclidean distance to things like Mahalanobis distance. Does that get used at all? Which is like weighted by some sort of covariance matrix or something?
Okay, so, I haven't myself actually used that as a metric, but as I said earlier, there are a number of variant metrics that one could use. So, and so I think from what you're saying there, I believe you're saying that that can somehow fix the scaling issue that typically is is what one sees with the Euclidean. Is that what you're saying?
Yeah, it's like a tweaked Euclidean.
Okay, yeah, true. Yes, agreed. Any other questions? Okay, thank you. Okay, so we've just touched on how to measure similarity between texts. Next thing we need to do is, prior to actually creating an embedding, your text is made up, it's come from some data generation system. It's probably corrupted with all sorts of weird characters, so there's a whole area of NLP where you need to kind of pre-process text to make it sort of, to kind of prepare it so that it's actually, in a form where you can truly pull out information out of it. So this is where the whole NLP pre-processing kind of step. This is where the NLP pre-processing step is required out of the pipeline. So generally, one of the things that one would need to do is you have your sentence. First thing you've got to do is tokenize it. You've got to pull out tokens out of your sentence. Okay? You might have some weird characters in there that have no meaning at all. Yeah? So, and if you leave them in there, they're just going to degrade, what you're trying to actually, the insights you're trying to pull out of the text. So again, you need to get rid of those guys. So that's what's called normalizing. Then, stock words. There's going to be a bunch of words in there. D, is, words that have, they're there, but they don't add anything. So you've got to get rid of all those guys. Yeah? And then finally, in some cases, there could be words that need to be stemmed or lemmatized. Yeah? And that's because, say for instance, you have run in. Yeah, you can probably stem that into just run, for instance. And again, what that does as well is that gets rid of a whole bunch of duplicates, because you might have a lot of these words which are just adding hardly any value, and they just degrade the sentence. So again, you've got to do all these steps. So essentially, the next slide here is just showing you that whole workflow that's required. So you've got to have a NLP pre-processing workflow. This is almost a sort of a given step that one must do, when you're trying to process text.
But are you not using some information in tokenization? For example, the DNA are quite important, unique, or one example of an object.
Yeah.
The apple, a apple, they're quite fundamentally different.
Okay.
You lose something fundamentally. I know what you're doing. We're stripping away losses. Long language is very complex.
Yeah.
Simplifying it, but you lose something.
No, true, and I think you're right. You're right. So I think the way for me to answer that question politically is to say you've got to do it in context to the problem that you're dealing with. Yeah. But I'm sure you agree with me that a lot of text generally has got a lot of irrelevant characters or tokens. Yeah. Okay. All right, thank you. Any other questions, actually? Yeah, thank you.
Can you say again what's normalization for you?
Normalization, I guess for me, would mean getting rid of, those kind of, those things you get when you, if you pull, say, something from the internet, and you've got those, those kind of anchor tags and all that. Yeah, all that stuff. I don't think they add any real meaning to, to semantics. Yeah, it would just pollute it. So those kind of things you want to get rid of. But again, to the gentleman's point, you've got to do it in context. It really depends on the domain that the problem domain that you're trying to solve. Any other questions? Okay, thank you. Okay, now we're moving on to the third sort of step. And this is the most interesting bit, really. This is now where we're trying to do feature engineering. So we've got a sentence, which is just text, but you want to use a machine to process this sentence so you can pull out some semantic meaning. So you've got to do something to that text. You've got to convert it into numbers. So there's a whole kind of history in NLP, which sort of tackles how does one sort of embed text. And for such a long time, until more recently, bag of words has dominated that space for a long time, maybe for decades, and has actually, has provided a lot of really, quite practical solutions. So I'm just going to walk you through that whole kind of evolution, and then how that got me sort of to where I am right now, where I've played around with a whole bunch of other technologies and got me to where we are today. Of course, Transformers is the new kid in the block right now, and that's sort of completely revisionized, NLP. It's got NLP to a level now where image was, maybe vision was, maybe 10 years ago. So, but I'm just going to try to sort of walk you through my experience in this space. So, of course, you have bag of words, or sometimes called count vectorization. I've not included that in my analysis because I just don't think it's going to add that much value. But I have looked at TF-IDF, which is a better form, which is one step ahead of bag of words. There's also word embedding, which 10 years ago was like the best thing ever in NLP, where you have a shallow neural net, and then you can train it to learn neighboring words, or you can train it to take one word and then, to take one word and then tell us the neighboring words. And then you've then had transformers. Of course, other things happened from word embedding to transformers, but I've kind of just ignored that. And you see here, this is not scientific at all, this is just my own kind of observation in the space, that this is the evolution of how I see things evolving in time and performance / complexity. So we started off with bag of words, which has been around for decades. Then you had TF-IDF. TF-IDF was trying to say, you can't assume that every single word matters, that some words are more important than others. And then you had word embedding. And then word embedding, there's so many variants to word embedding. Yeah, especially when you're trying to go from word embedding to sentence embeddings, because they're two different things. There's a lot of things you need to do. And then, of course, we've now in this brave world of transformers, and there's different kinds of transformers are out there, and they're doing a great thing in language, in language models. So let's just explore TF-IDF. So TF-IDF, the idea is you have a term frequency, and then you weight that term frequency, which is basically a number of times that word appears in the document, and then you kind of weight it against this IDF, this inverse document frequency. And that's to kind of modulate the fact that not all words, that some words might be irrelevant. And so you're trying to make sure that you're not putting too much weight on every single word, treating each word as if they're the same. And that's been great. Actually, there's still a lot of solutions out there which just use TF-IDF. And TF-IDF is a very cheap way to build an NLP solution, a practical NLP solution that works out there in production. And we've got some, my company, we use them, and it's been great. And in fact, some of my analysis later on indicates that TF-IDF has still got a role to play. Like when you compare it to the performance I'm seeing with some of the more complex models, I mean, TF-IDF has still got a role to play. Then we kind of moved on to word embedding. And word embedding now, I think, was a game changer. So this is the first time where you can now actually start to see real semantics in words. So the problem with TF-IDF is TF-IDF still has the problem of bag of words, because TF-IDF, you still have a very sparse matrix, a sparse matrix, and most of that doesn't really have as much meaning. And secondly, the other problem with TF-IDF is it doesn't really capture semantics in any way. When we then evolved to the point where we now have word embedding suddenly actually allowed us to get a shallow neural net, train it, and actually train it so that it understands words, words in its neighborhood. And that suddenly gave us the power of semantics, especially at the word level. And I think what I'm saying here is kind of just walking us through, some of the benefits of, word embedding. The fact that word embedding doesn't suffer this problem of sparsity of, your matrix, because your vocabulary generally is very, very large, and it's a very large matrix actually, because basically it's number of words in your vocabulary along this axis, and then number of documents along this axis. Sometimes this could be very, very large, and most of it is just zero. There's just zeros in there. It's sparse. With word embedding, when you train a neural net to spit out a word embedding, you basically predefine the dimension of the vector, and that's typically 50, 100, 200, 300. It's well defined, and so it's a much smaller vector that tries to capture semantics as well, yeah? There are variant word embedding technologies that are out there. The three most popular ones that we all know of is Word2Vec by Google. You have Glove by Stanford University, and then I think Facebook also have something called FastText. For the work I've done here, I've been using Glove, but again, I have used Word2Vec in the past, and I've also used FastText. So what is a word embedding? So here we can see an example where we've essentially embedded the word man, woman, king, and queen. Actually, this has come from a very kind of classic example for word embedding. And there you can see what we've done here is we've taken the word and we've now formed what is a fixed vector for those words. And the interesting thing here is that the vector is very dense. It's not a sparse vector as one would usually have if you're trying to do this with a bag of words or TF-IDF. And then what's interesting is that when you then take this, in this case, this 10-dimensional vector, and then convert it, do some dimensionality reduction into 2D, you can see that actually the word man and woman are kind of have a relationship, very similar to the word queen and king. So clearly, word embeddings provides us a mechanism to learn semantics, and I think that's what's demonstrated here. And then just to kind of go into a bit more what's going on underneath the covers, as I indicated earlier, word embeddings are using shallow neural nets. There are two typical, you could say, configurations. Oh, sorry.
Your last page,
yeah.
You had columns. So what are the column headers? What would they be?
Columns.
Yeah, you got man points.
Oh, sorry. So those are not actually really columns. They're just simply vector values. So in the first case, you got 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so that's an 8-dimensional vector. I mean, it's a hypothetical.
But what would they, so if they say 0.6, 0.7, what do they signify? Is there anything?
Okay, I see your point. What do they signify?
Model attributes they're trying to model.
I would say they're trying to model semantics, but in a kind of spatial domain. So if you think of, so how do we arrive at this is probably the question you want answered. So maybe if I show you this. So there are two configurations for creating a word embedding. One is called continuous bag of words, where you basically say, I want to predict this word because this word is surrounded by these other words, yeah? So that's called continuous bag of words, okay? So now you're predicting, so you're basically getting the machine to understand the connection between a middle word and based on its surrounding words. And then you've got this other configuration, which is doing the converse of that, which is basically saying that here is one middle word, I want to predict its neighborhood words. So to answer your question, that vector is capturing a spatial characteristics of where does that word fit in? What are its neighboring words? How is it close to its neighbors? And then it's kind of providing that in a sense. I mean, the outcome is basically some kind of semantic meaning right to those words. So far we've been talking about word embedding, but actually we want to solve a problem to do with sentences. So how do we go from a word that now has n number of, an n-sized vector to a sentence that maybe has many words, but we want that sentence to have an n-sized vector. So the most basic way to solve that is to just do an average. So you take each word that makes up the sentence, and then you simply just take the average of it. So let's say, for instance, hypothetically, let's say that the word, we created a word embedding of size 10, and let's say that there are 15 words in that sentence. Then you basically just take an average of all those 15 tokens, and then you end up with with a final sort of 10-sized vector. And that's the most basic thing to do. Now, the problem with that, though, is it's just an approximation, and actually has some flaws. And actually, at times, when you do this, you realize that the performance is not so good. And then a whole bunch of other tricks people have done where they've tried to somehow not just blindly just take the average, but they will do something similar to what you do in TF-IDF. They will try and weigh the values, based on, in fact, one solution uses the IDF portion of TF-IDF to sort of weigh the way you will, so you have like so you have a weighted average rather than a normal average, if that makes any sense, yeah? The one I found that was very powerful, and I checked this online and I did a lot of research, is this thing here called SIF. And down the bottom there is the pseudocode, how the SIF thing works. I mean, in a nutshell, all it's doing is it's still taking the vector per each word, but it's then still doing the averaging. So if you look at line number 2 there, what's going on there is it's taking an average, but this time it's doing a weighted average. And that weighted average, you can see there is some value A, which is some hyperparameter setting, plus divided by A plus the probability of the word, multiplied by the vector. That's the first bit you do. Then line number 6 is the other thing they're doing, where they're basically pulling the, using SVD, single value decomposition, to pull the first principal component, and then essentially multiplying that, so there you can see on line number 6, multiplying that by the vector, VS, and then they get this value, which is a lot better than just doing a naive average of the vectors. And actually, when I ran this, and of course, this is not new, this has been around for a while, you can read it up online, it actually provides much better results. And it's a fairly cheap calculation to do. It's not as bad, yeah, as going for a more complex transformer-like solution. Any questions? Sorry, I know I've kind of rushed through that a little bit. Yes, please.
Why is this called smooth inverse frequency? Because SVD doesn't seem like a very smooth operation.
Okay, why is it called? I can't answer that question. Smooth inverse frequency. I'm guessing here, smooth perhaps because of the averaging. So you're just averaging, but I don't know, actually, is the answer. No, I don't know. Yeah, probably needs to. There is a good paper. So yeah, if you read that paper, so it's called A Simple But Tough to Beat Baseline for Sentence Embeddings. Yeah, it's a seminal paper. Really, really good paper, actually. It explains the whole kind of concept behind this approach. And then some other chap a few years ago wrote a library called FSE, which tries to, so he tries to tune the because trying to solve the PCA, sorry, the SVD bit of the problem is very expensive if you try and do it natively. So he used Python and a whole bunch of things to kind of speed up that process. So if you use his library, which is what I did, the library is called FSE. It's quite fast, right, to compute this. And what he's done is he's basically extended Gensim, which is a library for doing NLP, for doing word embedding. He's extended that library so that you can also do sentence embedding with it as well. Yeah. Does that answer your question? Sorry. Well, maybe not. And here's the sentence embedding basically. It's just an example of what it looks like. Typically, it will be, of size 300, depending upon, so it all depends on the baseline embedding you're using. So in my case, I'm using Glove, and I was using a Glove, I think it's Glove 300. Again, they have all these numbers just to indicate the size of the vector for each word. So I'm using a Glove word embedding, and then I've transformed that word embedding into a sentence embedding. And of course, it's gone through this whole process of SIF, which spits out almost like a resultant vector for the whole sentence, rather than the individual vectors of the words in the sentence. Does that make sense? Yeah. Okay, cool. Okay, so far we've talked about word embedding solutions. So we started off talking about the more rudimentary TF-IDF, which, as I said, is still being used in many, many solutions, and it still has a place. Then we talked about word embeddings and variant word embedding solutions. Now we're going to move on to the brave new world of transformers. And I'm going to talk about two well-known, quite popular technologies now. One of them is by Google. It's called USE, which stands for Universal Sentence Encoder. It's a very, very powerful tool, and actually quite fast. Once you've downloaded the language model, it's really fast. And really, what users doing is basically in the black box is just saying you give it a bunch of sentences and it spits out, the vectors, the embeddings. That's what it's doing. Pretty much what I've shown here. And how does it work? So Google have 4 or maybe even 5 now, 5 versions of USE, and I think they've kind of progressed in time. So I think the versions are based on the primarily based on the architecture of the neural nets they're using. So I think Google are using 2 variant architectures. One is a transformer-based architecture, which is what's shown here. So I'm not going to go into too much details, but basically that's just it's shown there pictorially. And then the other one is based on a different architecture, which is a deep averaging network architecture, which is what's depicted here. Yep. Again, if you want to know more about this, please feel free. If you go onto the TensorFlow website, they've got some really cool tutorials there on on the inner workings of these. And there's also a paper, which I think is a very famous paper that Google wrote on this. This came out in 2018, I think. And then here I'm just showing you some of the library details, how you can run it. So it's just a few lines of code. You just import TensorFlow. You import TensorFlow Hub. TensorFlow Hub is the repository of the actual model, language model, and then you just call that. And here I'm calling, you can see that I'm calling version 4, and then you just simply call an embed. You have a wrapper method, embed, and then that just calls it, And then essentially you can then just run it, by saying embed, give it the sentence, and then it spits out a vector, a tensor basically, spits out a tensor. Okay. Then the other transformer-based solution that I looked at is this thing called, the group is called S-BERT.net, but their library is called Sentence Transformers. Actually, it's a really, really good solution. And what they do is they're leveraging Hugging Face's models, basically, So they've just written a whole bunch of infrastructure around Hugging Face, making it a lot easier to use Hugging Face. Sorry, guys, apologies. Do you all know what Hugging Face is? I mean, Hugging Face are like the big guys right now who are doing all the NLP stuff. They've got some cool libraries, making it very easy for us to do NLP. So they use a different architecture known as the Siamese twins architecture, which is shown here. I guess it's Siamese for obvious reasons. So you have two legs. One is for one sentence, the other is for the other sentence. It goes through a BERT transformer model. That embeds it, and then it then goes into a layer with a cosine similarity layer, and then that spits out. And then that predicts, or kind of trains a model, tell you if the words are similar or not similar. And then you measure similarity as a cosine metric between -1 and +1. Yeah, that's kind of how it works. This is very good. My only experience is it gives you the better, I think out of my, when I did my analysis, this model had a better performance, just in terms of when you compare the outcome with respect to a benchmark problem. This had a better performance, even much better than Google's USE. But my findings with that is slightly slower than the Google's solution. So you probably got to find a trade-off between performance and speed. And again, this is the API. This is how you would use it. So again, it's very, very simple to use, right? They've stripped out a lot of the complexity, so just a few lines of code. So you basically import, import the library, sentence transformers, and then you also call the Hugging Face library that you want to use. So in this case, we're using a mini LM, okay? And then pretty much, again, you just say model.encode, and it spits out numbers. Okay. I'll just pause there for a minute, because I think I've rushed this a little bit. So any questions? Yes.
I have a question about the dense vectors. So I understand that the bag of word provides sparse vectors.
Yeah.
While the word embeddings are dense vectors. Which
Correct.
is why the word embeddings are better than bag of words. But can you clarify a little bit why the dense vectors provided by word embeddings is less effective compared to the dense vectors provided by transformers? Since they are both dense vectors, so what's the difference in the output that makes one better than the other?
Okay, let me try to understand the question. So first of all, do you agree that bag of words and even TF-IDF, what it spits out is an embedding that is very sparse? I mean, if you look at it, if you ever open it up for a real problem, not a toy problem, there's a lot of knots inside the matrix. Yeah, a lot of it is just it adds no value. So inherently, that's not going to give you a very good performance. Yeah, agreed. Okay. Now, word embeddings provide a dense vector per each word. Yeah, they're dense. I mean, that you will predefine it. When you train the model, the shallow model, right, to spit out the word embedding. And typically, you set it to 100 or maybe 200 or 300. Typically, it's 300 or maybe sometimes 500. Yeah, is the number of is the length of the vector. So inherently, that's very dense. Okay, and actually, when you do the evaluations, you run sample problems. You see that word embeddings generally perform better than bag of words or TF-IDF. Are you now? I'm not sure if your question was that when you now compare word embedding solutions with the transformer solution, are you saying that sorry, I was trying to understand that question. Yeah.
I was basically just referring to the bag of words for context.
Yeah.
The sparse vectors are said to be less performant compared to the dense.
Correct.
But then when we try to compare the embeddings provided by SIBOR, for example, which is a dense vector,
Yeah.
to the embeddings provided by a transformer, which is also a dense vector.
Yes.
They are both dense vectors.
Correct.
So what makes the dense vector provided by one better than the other?
Okay, I see. I would say in general, again, I'm generalizing it, transformers definitely outperform everything else in general. That's my observation. Yeah, transformers. So if you're looking at S-BERT or you're looking at USE, which is the Google one, those will always outperform other solutions. Yeah, generally. Yeah, and then word embedding, as I said in my when I described the solution, word embedding is almost like an approximation, because remember, it's a word embedding. So those embeddings, those vectors only apply to words. So you then have to somehow figure out how to, utilize it in the context of sentences. And that's partly why we average it. So averaging gives you a slightly better result, and then the variance of how you average it. Maybe you do a weighted average. And then one of those is the SIF, the smooth inverse frequency. That gives you a slightly better, actually, a much better solution than just averaging. But definitely, if you compare word embedding to transformers, I think transformers definitely outperform word embeddings in general. But it's always a trade-off. So, if you're building a production system, like most of us probably do, sometimes you haven't got the, you've got to do a cost-benefit analysis. If it's going to cost you X amount in terms of compute to use a transformer model, maybe you're doing this on the cloud, and it costs you X amount to buy that compute, it might be better, even though it might give you perhaps perhaps the performance might not be as good as a transformer model, but it might be cheaper and much more cost-effective to go for a suboptimal model, but that's quicker. So these are the kind of cost-benefit analysis that one has to make. In fact, I had one case where I was using a transformer model, and this was on Azure, and it was just taking too long, and it was very expensive, and I resorted back to TF-IDF. TF-IDF was much quicker, it was cheaper, and even though the results were not as good as a transformer model, it was a lot quicker to run. And so I'm not sure if that answers your question. Sorry. Okay, cool. Any other questions? Okay. All right, so I guess the next thing we want to do now is, now that we've established that we can build embeddings for sentences, and these embeddings are dense vectors, we still want to somehow visualize. We want to see, put some kind of understand what these vectors really mean, perhaps in a kind of spatial domain. And typically, for us humans, that would be two-dimensional or maybe 3D. So really, the next bunch of slides is going to go into how can you visualize these embeddings. Yeah. So what I've done is I've looked at providing like a scatter plot so we can see the embeddings in 2D. I've also provided another plot, like a heat map plot, so that we can actually also look at, once you've got these embeddings and then you use them to compute similarity, maybe you can produce a similarity matrix, and then you can also then look at that as a heat map. So, these are the kind of things I've done to kind of analyze my results. And then with respect to the embeddings, obviously they are n-dimensional in size, but we need them to be in 2D. So obviously we need to come up with mechanisms that allows us to reduce the dimensionality of the problem into 2D space. And of course, you start to look into some of the classical ways of doing this. So one classical way is, PCA, principal component analysis, which is a well-known thing. Again, scikit-learn has got everything in there. So I've used PCA, I've used multi-dimensional scaling, MDS. I've also used another popular one is t-SNE, t-distributed nearest stochastic embedding. And then, of course, there's another one I also saw, which is this UMAP thing. So I'm just going to kind of quickly walk you through what those are. So again, all of these libraries are out there. It's all freely available. The first three are in scikit-learn, and then UMAP, you can just do a pip install, and you get UMAP. But these, I tried all these four just to see how, and they do have some subtle differences, yeah? But they tell you different things, but they're generally all good. PCA, obviously, is linear. So PCA is probably the weakest out of all four. So here's a schematic depiction of the of a TF-IDF embedding. This was for a problem that I described earlier, the book title problem. So this is me just simply, looking at, an embedding, sorry, embeddings of the corpus, So basically in here, the numbers relate to the sentence ID. And there you can see that documents which are similar all congregate in one cluster, and those, obviously, those which are not similar in different clusters. And this is how you would typically, if you do PCA on the embeddings, this is what you will see using PCA. And by contrast, this is me now using t-SNE as my dimensionality reduction technique, but now I'm using SIF. SIF is the thing I described earlier, which is the word embedding thing, and there you can see there's a subtle difference in the way it's sort of providing a spatial representation of the embedded sentence vector. And again, just for completeness, this is this is the USE. USE was the Google solution, Universal Sentence Encoder, and here I'm using MDS. The reason why I'm doing it this way, because I can't print out every single use case because there's a lot of different combinations. So I'm just printing out, some odd ones. But there you can see that they all tell you something. I mean, each use case is telling you something, but it's just that the way things are spatially represented will be different because the dimensionality reduction techniques are slightly different. Yeah, but they kind of still provide you insights. You can see that they're clustering of documents, and that tells you that those documents are going to be the ones that are very similar to each other. And this is S-BERT. So again, here, the embedding approach is using the S-BERT transformer model. And here I'm using the UMAP, sort of two-dimensionality, the UMAP dimensionality reduction technique. Okay, next bunch of slides. Yes.
You just showed quite a lot of different visualizations of different combinations.
Correct.
Did you do a comparison between these different combinations? And did you find anything interesting by doing so? Any consistencies, strong inconsistencies?
No, it's a good question. Anecdotally, I think I did by just looking at the the visuals. But if you're saying did I quantify any differences, no, I didn't. However, what I am going to show you towards the end is I did quantify the differences between the 5 different embedding techniques, and I will give you those numbers towards the end. Yes.
Which one of these would you use to featureize a sentence vector or a sentence embedding or a word embedding? So let's say you have a model, but you don't want to have 500 dimensions.
Yes.
And you want it to be, you don't want that many weights.
Okay.
And you only want 2 dimensions. But like, which one of these would you use to compress down these 500 dimensions to 2?
Okay. So it's a good question. So in this context, I was only reducing the dimension purely to explore spatially the representation of the vector. It wasn't because I was trying to do clustering or this sort of thing. No. It was purely for me just to kind of just to study the spatial representation of the vector. So I'm not sure if your question is that which model would you use for embedding? Because there are 2 kind of decisions here. First decision is how do you embed your data? Do you want to embed it using any of the 5 approaches, from the simple TF-IDF to the more complex S-BERT? You've got to make a decision. And that decision also is also predicated on computing costs. Yeah? Okay. And then second decision is, depending upon your problem, what problem are you trying to solve? If you're trying to simply solve the problem of trying to measure similarity between sentences, then really, you don't need to do any dimensionality reduction. I did it because I was trying to understand the spatial representation of the vectors. But if your problem does require you to do some kind of clustering, and you want to take a very massive, dimension vector and turn it into something smaller to enable you to do clustering, then yes. My advice would be, I would say maybe t-SNE is a more popular one that people tend to use these days. Yeah. But that's just my, I think again, to the gentleman's question earlier, it's subjective to the domain and problem you're trying to solve. Yeah. Yes, please.
Which metric did you use for TSNE? Did you use a Euclidean distance or did you use cosine?
Okay, good question, good question. Yeah. Sorry. So I know I started off by talking about similarity metrics, Euclidean, cosine, and Jacquard. Yes. After doing that, I kind of just decided on using cosine. Anyway, cosine is the most popular way of measuring, sentence similarities. So yes, cosine. Yeah. Any other questions? Okay. So, sorry, did I answer your question? Did I try to answer your question at least? Oh, sorry, the gentleman, did I answer your question or? Okay, thank you. All right, so I guess the next thing now is we've just looked at a scatter plot just to see what happens when you kind of compress from an n dimension to 2. The next thing we're going to do now is we're going to take the similarity measures that we've just done, but this time we're going to do it as a matrix. But I cheated a little bit. So rather than do the whole matrix, so typically, let's say you have a corpus, hypothetically, a corpus of 10 documents, 10 sentences. Then typically, your similarity will be 10 by 10. So it means you have 100 points. But actually, because it's a symmetric matrix, you don't need to do all 10. You only need to do half. Yeah? Because number one, you don't need to do document 1 against document 1. You don't need to do that because it's going to be 1. We know it's going to be, yeah? If you compare itself by itself, it's going to be 1. Then secondly, let's say you have document ID 1, document ID 2. The similarity between document ID 1 and document ID 2 is a value A. Equally, that value A is also the same as the similarity between 2 against 1. So that's why, if you look at this matrix here, half of it is completely black because, it's blank, because it's essentially a cross value of the other. Yeah, does that make sense? So it's just a way to save time and compute. So I'm going to walk you just very quickly, walk you through some of the findings. Again, anecdotal. I haven't measured anything. I'm just simply visualizing. Okay. So first one is the heat map for TF-IDF, where I'm just looking at the TF-IDF embedding for the book problem, the book title problem. So again, you can see there. Obviously, you can see that bits are lighting up where there's similarity, and the bits where it's really dark means that it's not similar. The next one is a heat map where I'm using SIF. By the way, this one I showed you earlier is TF-IDF, and I said earlier that TF-IDF is probably the least performing out of the 5. Okay, so please, just don't forget that. This is the SIF one, which is the word embedding variant, and again, same problem. So we've applied SIF on the same problem, and we've just plotted out the heat map. And then this is, again, doing the same, but this time using a transformer model, the universal sentence encoder. And there you can see, actually, it's interesting to see that, actually, the USE, again, if you compare that with this, it's roughly, kind of looks the same, but it's not necessarily the same. I haven't measured anything here, but just visually, it kind of looks the same. Or at least there's some similarities between the two profiles. And then finally, this is where we're using S-BERT, again, on the same data, and plotting the heat map. Any questions on this one? Okay. Right. Now, we've done a number of things. We started off by trying to understand what is STS, sentiment textual similarity. We looked at how to compute similarity. Do we use Jacquard? Do we use Euclidean? Do we use cosine? I then settled on cosine. Then we took the problem to another place. Now we then said, okay, how do we actually encode text information? How do we encode textual information? We then looked at a number of options, 5 different ways to do this. We looked at the very kind of simple but very effective TF-IDF. We looked at two variant word embedding approaches. One is a very simple one, averaging. The other one is the smooth inverse frequency. And then we looked at the Google's universal sentence encoder. And then finally, we looked at the S-BERT model. What I want to now show you is how do we actually validate the performance of these 5, and these 5 models that we've looked at. Yeah? So one way to do that is, first of all, you've got to have the right problem to solve. So I guess, in my case, I've, again, just looked at what's been done in the, in the domain, look at the research, and actually for a number of years, they ran this thing called, the STS benchmark problem, where a bunch of academics in the field, experts, will take these problems, well-known problems, and they will build models and then essentially validate the models to see if they are performing to a level. Almost like Kaggle, where they will have a lead board and they will figure out if which model has got the highest metric, in the ranking order. So one problem I looked at was this thing called the sentence pair problem. Yeah, the sentence pair problem. And what that does is it's basically about 2,000 or thereabout rows of data where they have two sentences. So, and the idea is to compare one sentence against the other sentence. And then what's also cool here is that they also provide you with a label. So there's a label between, I think it's between 0 and 5, a score. Yes, it's a floating, a double or a float, yes. So it's basically between 0 and 5. And then what you can now do is you can take your model and then you can plug in your, you can read each sentence and then compare the similarities, get the number that you get, and then compare your number against their label number and see if your number correlates with theirs. And you can see here that what they're using here is not accuracy, they're using correlation, because their score is a value between 0 and 5. And that's kind of why for this analysis, they've used the Pearson correlation metric. So what is the Pearson correlation metric? Let's look at that. So Pearson correlation metric allows you to take two vectors, x and y, and compare them and see if they correlate with each other. So if the value is 1, it means there's full correlation. If the value is 0, it means there's no correlation. Yeah, that's basically what Pearson, and all it's doing is it's basically solving so the denominator is the covariance matrix of x and y divided by the standard deviation of x multiplied by the standard deviation of y. And then, so that gives you a nice metric that allows you to compare A against B. Any questions? Okay, so, oh, sorry, yes.
Yeah, sorry. There's some implicit assumptions in choosing Pearson. So why not choose, say, S-BERT, or what did the p-value look like for Pearson?
Okay, that's a good question. It's a good question. Actually, in the entire analysis, yes, they do use, I think it's called yes, that's right, where they use that as well. I've just settled on, so they use Pearson as well as, and this other variant of it. I've just used Pearson, purely in the interest of time. I had to get some numbers out. But I noticed that if you read the papers, some of them tend to use Pearson quite a lot, actually, yes. However, you're right, yes.
It kind of makes assumptions about the distribution, right?
Correct, so this makes assumption that the distribution is, it's normally distributed, correct. Yes, so part of this is that you assume that that data is normally distributed, correct, that's right. I would say yes, it approximates to normal distribution, correct, yes. I mean, in machine learning, we have to start with some sort of approximation of our distribution, right? I mean, generally, we always start with a normal distribution as the kind of as the hypothesis of our data. But I fully agree that you can use other metrics. But if you read the analysis for the benchmark I used, Pearson was, what the developers of S-BERT, for instance, and even the Google's they both use Pearson. I think Google used Pearson as well as this other correlation metric. Not sure if that answers your question. Does that answer your question? Yeah. Okay, thank you. So the next slide I'm going to show you now is essentially, what were the findings that I got when I used the Pearson correlation matrix as a way to validate which one of these 5 models performed better. And that's the results there. So clearly, S-BERT kind of won the context. And then next was use. And then, of course, as expected, SIF was third. And then the averaging technique was not as good as SIF. And then, of course, right at the bottom was TF-IDF. Now, I'm guessing that gentleman, I think that your stats is probably better than my stats. What I notice is that the p-value, which is a way to kind of, to reject or accept the null test. So at the null test, using a Pearson metric, is that the things are not correlated. But that's the null test. But actually here, the p-value was 0, and typically you would check to see if if the p-value is basically less than 0.05. But in this case, it's 0. So I'm guessing it's indicating that there is some correlation between the two. It's just that the correlation is kind of deviates from one technique to the other, and that the best technique seems to be the S-BERT.
Because we want to see a scatter plot.
Probably, yes, correct. Any other questions? Okay. I think we've spent over an hour just me kind of rambling and talking about stuff. I think the next bit now is I wanted to just kind of walk you guys through the 3 demos, and that hopefully will crystallize some of the things I've been discussing, because then you can see code and you can actually see that this is not all waffle. It's not just theory. There's also some code I've written some code that kind of spat out some of the results. So I think that's the next thing I was going to do. But before that, any questions before I kind of get to that bit? Okay, cool. So before I go into the code, maybe I just kind of walk through each demo one by one again. So the first one I mentioned earlier is the book title problem. And the idea is that you have basically a list of books, titles, and the idea is you select one title, and then you compare that guy against the rest of what's in the corpus, and then you see how close is that title to the rest of the titles in the corpus. It's very simple. And then all I'm doing there is I'm then splitting out. I'm trying out different metrics to measure, the similarity. As I try like cosine, Euclidean, and Jacquard. So let's start with that one. And again, all of this stuff is on Git. Hopefully you guys have got the repo. Unfortunately, I think if you try and run it, you have to make sure you've got so it's got requirements.txt file. So you have to install all those libraries. Now, I was speaking to a gentleman earlier today. In hindsight, I should have probably created a container so that it's all self-contained, and I just put it in Git, and then you guys can just download it and then run it on your machines and not have to worry about all of the dependencies. But now you have to run the requirements.txt so you can load all the dependent libraries. Yeah. But I might probably go back and see if I can simplify that. Maybe I'll put it into Colab and then just give you guys the URL of Colab, and then you can just run it yourself in Colab if you want to explore it any further. Yeah. Okay, so the first one, I'm just going to quickly run the first guy. So that's this one here. That's the problem here. So actually, before I do that, let me just show you the structure of the code. So basically, the code is made up of this guy here, problems. So inside this folder are the 3 problems that I'm trying to solve. So one of them is the book title problem. The other one is the querying, the very simple sort of toy sort of querying application that just, what do you call it now? Basically, you give it a query, and then it goes and finds the closest documents to that query, yeah? And then the third one is the actual benchmark thing that I showed you earlier, yeah? So I'm going to start off with the book title problem, okay? Just maybe to show you a bit more of the infrastructure. So I've got a bunch of modules in here that helps me do things like NLP processing. So I think earlier, oh, sorry.
Can you change it to a light theme? Because that's really difficult.
Oh, is it? Okay, all right. How do I? Okay, now you got me. Okay. Okay, let me try. Let me see if I can do this. So settings, appearance. Is it this one?
Search for theme in
Okay. Here? So you want it to be this guy here? Like that? Wow. Really, really. I've not used this in ages. Okay. Yeah. Is that better? Okay, all right, cool, all right. All right, sorry about that, yeah, okay, all right. So, so I've got some basic helper infrastructure components, like NLP preprocessing, and so that lives in here. That's just a class that provides me, I think I talked about all these things, tokenization, getting rid of lower casing, noise removal, blah, blah, blah. So that's just a class here that just does all that, yeah, just cleans up everything for me. Yeah, so again, I'm not gonna bore you with all that detail, but basically it's just a cleaner. A bit of logic to do that, and everything has got tests, so it's got unit tests to show you how to use it. Okay, then most of the heavy lifting actually is inside here, this feature extraction module, and in here is where I've got all of the different embedding methods, from the very basic TF-IDF to the more, more complex or more interesting S-BERT. Yeah, and then these are all wrapper bits of functionality that allows me to kind of call those things. All within the class. So again, I'll let you guys spend your time and look at, I'm not going to bore you with that, but what I will do is I will try and run this now in situ. So I'll run each problem one by one. So the first one is going to be this guy, okay? And this guy is in a class. So obviously these are all my imports. So these are all the standard imports. Okay, actually this should not be there, that's a mistake. That's a unit test, which I'm not using here, but I was using it before. But basically everything else are all the standard imports. And then down here, all my own kind of custom modules that I've used. Yeah, some of them are helpers. And then I've also got login switched on here. Yeah, just a simple login. And then this is the constructor of the class, which will run the demo. Okay, and then inside there's a bunch of methods to do different things. One to initialize so earlier I think I showed you the fact that I plot a scatter. I do a scatter plot, and I also do a heat map. So all of that is driven by this initialize visualizer. Okay, and then I've got a bunch of things here just to run different use cases. Yeah, and I'll just run those. I think it's better if I just run them and then you see them in action. So I think I'm going to start off with just computing the similarity metrics. So hopefully it won't take too long. Let's see. Okay, while that's going on in the background, I don't know if there are any questions from anybody. Yeah, of course.
You worked on the CD in your job.
Yes.
So what's your advice for hacking these systems?
I'm not going to answer that. I'm not going to, okay. Can I defer, not answer that question? I don't get into trouble there. So although I said, I work for Credit Suisse, I mean, that's my day job, but everything I've said here today has no implications on Credit Suisse. Yes, I work as a data scientist. I lead a team at Credit Suisse, but everything I'm doing here, this is my own kind of indulge. This is my own sort of personal thing, and yes, I did work on a project to do with CVs, but yeah, no comment on that one. All right, so this is the results I showed you earlier, but here you can see it in situ. So there you can see all it's done is it's looked at. So this is the query up here. This is the query, just a single list. That's the query, and then it's going to query all of the. Is then going to apply that across this collection of titles, yeah, and all of that is inside. This was pulled from the data that I sourced online. Yes, yeah, and then all it's doing here is just ranking the scores for each of the different similarity metrics. Yeah. So this you've seen already. Yeah. So again, that's that demo. Please, in your spare time, play with it, hack it, break it, whatever. Yeah. So, and that's the first one. Any questions on that before I move on to the next one? Okay. The next one I'm going to quickly look at, and I'm not going to have time to run every single use case, but earlier I think I showed you the scatter plot and the heat map. All of that is done with, with each of these guys here. So I'm just going to run, maybe I'll run the, let me see. So I'm going to try and run, let me run the SIFT example. So I'm just going to, again, I'm not running all of them at the same time, so I'm just going to run this guy here. Hopefully this won't take. So this is the word embedding example. So what this is doing is it's picking up a pre-trained glove embedding, and it's going to then augment it by applying the SIF thing I talked about earlier, the smooth inverse frequency, and then turn it into a sentence embedding, okay? And then use that to then do, to do this. So here again, you've got a bunch of queries. So you've got one column is the query doc, apologies, and then other column is the current doc, and then it's just measuring how close are they to each other. So obviously one means that these two are the same, and then it's, again, let's take another one. So let's take a case where it's not very close. So if you look at Harry Potter, blah, 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 there, and then compare that with this next guy here, you see that slightly close, but not very close. And so again, that's 0.75. Actually, I mean, I should have rounded those to 4 decimal places, but I didn't do that yet. Yeah? So again, that's all that's doing there, is it's just taking, so again, nothing really special in a way, other than that I'm using a different way to embed the sentence, and then I'm just comparing similarity against each other using cosine, similarity. Yeah? Okay? All right. Sorry. One more thing. So, and then in the background is spitting out the heat map. So again, that's the heat map for the similarity matrix, or the lower triangle, the little bit of the matrix, yeah? And then also it's spitting out the scatter plot. This is MDS, so it's spitting out the scatter plot, and then there you can see, and actually it's interesting, so if you look at the results, you see that, so let's just take one example. So if you look at 10 and 11 should be pretty much the same, so let's look at the result. Because here is 10 and 11, there is 10 and 11. You see 10 is on top of 11 there. So now if we look at the actual result, 10 and 11 are 1. So that's 10 and 11, so obviously that has worked. So that's 1, yeah? And again, you can spend your time and just look at it, and you can see that where it's clustering the doc IDs or the sentence IDs together, where they're close, would typically be the ones which have, similarities close to 1. Yeah? Okay, cool. Any questions on that one? Okay, let me, in the interest of time, I will move on to the second demo. Okay, so I'm going to move on to, I'm going to move on to the next demo. So the next demo is, let me close this guy, is the query problem. Okay, so this is the search engine problem, yes. So it's a very kind of rudimentary search engine where I'm saying, here's a query, a word or something, or a phrase, and I want you to search to find similar documents or sentences to this word. Yeah? So again, I'm basically saying that here's my query, I'm going to embed it using any one of those methods, and then I'm going to then compare that embedding with the embedded list of sentences, and then measure how similar the query is to the rest of what's in the, and then rank the top 10 and see, yeah, okay, cool. So that's the next one we're going to do. So for that one, I'm just going to run this guy, I think that, yeah. So here, the query document is this phrase, computer programming, and here I'm using the classical, the classic 20 news group datasets. I don't know if you guys know about that. It's in Scikit-learn, it's in quite a few places. It's a really good data set. It's basically 20 different themes from religion, science, space, whatever, and it's a very rich data set, and it's been used to typically to profile NLP solutions. So I've used it for doing clustering, to kind of prove that my clustering model works really well. And in this case, I'm using it to actually prove that my embedding is working properly. So I'm going to run that right now, and then. So hopefully this will be quick. Most of the time is spent in loading the language models. In this case, it'll be trying to load the Hugging Face. Hugging Face's language model, which is what the S-BERT is using. So that's, and it's quite a big data set. Yeah. Okay, and it's now done. It's finished. And let's see what the outcome is. So here, okay, it's very long. Okay, this was a bit tricky because the data is it's actually more than, it's not just, the sentences are quite big. Yeah, they're huge sentences, and some of them are actually paragraphs, actually. So what I've had to do is, originally I was going to display the original sentence, but I suddenly realized it's going to be very hard to display that in a table like this. So what I did was I had to apply the cleaning function on it first. So that got rid of all the unnecessary things we don't need in the sentence, and then that allowed me to manage it this way, which is probably why you can see here that the sentences are not totally grammatically correct, because it stripped out some words already, yeah? However, the semantics still remains. Yeah, it's still there. So you can see the idea is that in here, each of these sentences, it has some affiliation with the query. Remember that the query was about computer science. So let's go back to the query. So right here was the query, computer programming algorithms. So now in here, is there anything in here that relates to, computer programming? And if you look at it carefully, let's look at this one here. So that's, okay, let's see. So these are all technical terms. Just going through here. So semantically, there are some terms in here which relate to computing. Yeah, you can see that algorithm. Let's see. So again, algorithm there. Yeah, systems, pointers. Yeah. Yeah. It turns out that I selected this query randomly, and obviously it's not as close, so which is why the top score is 0.66. But you can see, again, if you spend some time, if you look at the top 10 that it's recommended, or that it's kind of decided close to the query, they all kind of have some affiliation with computing. Yeah. So it's another way to kind of build a very simple search engine. Yeah, if you wanna. Yeah. Okay, that's the second demo. I want to say any questions, but I don't think we've got that much time. So I'm just going to go on to the last demo, and that's this one. So this is the demo where I'm now just essentially just running the STS benchmark, and I'm trying to see which one out of the 5 techniques, out of the 5 embedding techniques has performed the most. And then I'm using the Pearson correlation metric as a way to decide which one is the better one. So again, you've seen that prior, but this is just me running it now in situ. This will take a couple of minutes, only because I'm running all the models together, especially the Google's Universal Sentence Encoder, as well as S-BERT. Yeah, they kind of have to read in the whole model in memory. Yeah. Yes?
I think for BERT,
Yeah.
for the Universal Sentence Encoder,
Yeah.
one doesn't need to pre-process the text, right? Because it will do it for you.
Sorry. So what's the question again? I don't think I got it.
For BERT,
Yes.
Universal Sentence Encoder, if I'm not mistaken, one does not need to, the text pre-processing is not a requirement.
That's an interesting point. Generally, you're right. With transformer models, generally, they advise that there's no need for you to to do any pre-processing. So yes, you're right. So, and since those two are transformer models, perhaps. In my case, I was running the same corpus that was cleaned across, yeah. So these results relate to cleaned sentences.
Because I think there is actually an argument against doing it.
Correct. Yes. Yes. Yeah.
When I use
True. No, it's true. It's true. You're right. Yes. Okay. Ignore that error. That's not my error. That's TensorFlow. Trust me. That's not my. But it did spit out the results, which is down there. Okay. And again, those are the results. So on that basis, guys, I mean, that kind of completes my, my talk. I really enjoyed the session. I mean, I can't believe it's an hour and a half. It's been really, really cool. And apologies if I'd rushed over things. I was trying to get a lot across. And the code is already on repo, so please have a chance to play with it. And I would try and see if I can push it onto Colab, so you guys can just run it. Because Colab would have all the dependencies. Yeah? Yeah, I did in the stack. Yeah. Let me, okay. Yeah, sorry, Slack, yeah, it's there. So guys, thank you very much, and thank you. Thank you.